Fantastic. Great. Okay, so hi everybody. My name is Mircea Zloteanu, and today, instead of presenting research like most of you have been doing, very nice research, very interesting indeed, I'm going to be talking about improvements that can exist in terms of how we analyze data, especially deception data. So the focus that I normally have is on human detection. So how do people detect if other people are lying or telling the truth? And I'm going to propose a new method. Well, it's not new, it's just one that we don't really use within our field that might be relevant towards understanding better what people are actually doing. So I'll state the problem the way I see it currently within the field. So one of them is that I think there are a bit too many researchers' degrees of freedom when it comes to the way we process the data that we collect from people. So this is both how we transform the data, the fact that we're aggregating a lot of it to the point where a lot of the interesting variance goes away and cannot be analyzed. We tend to be reporting at least 4 unconnected analyses in terms of we're making the reader make the connections without it being any way of statistically analyzing it, instead of simply producing one analysis, which is the one that I'll be talking about today. We often ignore the design structure of our study. So as I said, we might have nested structures, like participants are looking at different things. We have different groups of participants, and that can't always be captured by the simple models that we've been running, like ANOVAs and t-tests. And we are losing a lot of very important information about variability, which we could be analyzing and be reporting on it to have a better understanding. So a few of the talks before me focused exactly on the differences between liars, but also potentially between judges in terms of are some better, are some worse, are some more biased than others, and in what ways. And finally, I think that this is hampering a bit of our ability to build theory, because we're kind of stuck within this specific framework that I'll be presenting in a bit. And we haven't really been going beyond this. So we still analyze percentage data with ANOVAs and are trying to make inferences about this. But realistically, most of the studies within the past few years have stayed more or less the same. So just to set the scene for those of you that don't do this kind of research, or those that are planning to do research in the future, this is what I consider to be a typical deception experiment. So we present people with a video one at a time, and then we essentially give them a lie or truth button that they can press, or maybe we give them 3 buttons. So one of them that says, I don't know, or maybe we give them an honesty scale so that they have a wider range of values. And then just for good measure, we also give them a confidence scale that they can respond to tell us how confident they are in their decisions. But then is when the interesting part happens. How do we process this type of data? We normally start with entering about 1 row for each participant, and we just say, what responses did that person give? So is it lie or truth to each one of the videos? So in this case, let's say they were watching 4 videos. Then what we do is we try to match the veracity of their responses to that of the video and say, is it correct or incorrect? Afterwards, for some reason, we tally these responses to have a column that says truth accuracy and lie accuracy. And then for good measure, we turn these into percentages to analyze them and present them in a way that we feel is easier for the public to kind of understand. But we're not done yet, because we do the same thing for the bias analyses, where we look at the values and then code them normally as something like -1 and 1. And again, we tally these to have an insight into people's response bias. And then we probably also do this as a signal detection model by manually computing all of these values to try to separate accuracy from bias, or maybe because the reviewer told you that you need to report one of these on top of your other analyses. So we basically have done at least 4 analyses that we have to report. One on accuracy, which we might say, oh, we found an effect of accuracy within our study, but then we have to enter the caveat of saying, but actually there might be a bias situation that might be explaining that. Then we report the bias analysis and we say, yes, indeed, we did find an effect of bias. But now the question is, does the bias explain all of the accuracy differences, part of it? Does it go the opposite direction? What is actually going on? So we make people also look at the signal detection version. Let me see if I can get a little red filter thing. So then we also look at the signal detection one and the bias to try to get a bit of a better understanding. The problem with this is that the first 2 can be completely misleading, if not outright incorrect, and I'll explain that in a second. While these ones, they can be seen as okay-ish because we're analyzing them using ANOVAs, we're missing out on a lot of the variability and insight that we could be getting in these types of analyses. Now, why do I say that ANOVAs are not fit for purpose in analyzing deception research is because of the type of data that we are actually collecting. So either we treat the responses people give us as counts. In that case, they're probably not going to be normally distributed, which is one of the assumptions of the ANOVA. It's going to be bounded between 0 and how many videos you're actually showing people. If we convert them into percentages, they're still bounded, now just between 1 and 100, and they're also not going to be normally distributed because normal distribution does not have bounds. It can go to minus infinity and plus infinity. And all of these percentage ranks that we have are going to be dependent on how many trials you have. So sometimes you might have fewer trials, so your data is not going to look like anything that your models are expecting. And even if you have more trials and it kind of looks normally distributed, as I said, it's still bounded. And just as a little aside, not all percentages are actually the same thing, even though we might have a column that simply says percentages. So if it's something that comes from an overall circle, so let's say a slice of pie, that's an unbounded continuous variable. And normally it has a different standard, a different way that the errors might be distributed. So in this case, they might be normally distributed, but might not. So you might use something like a beta regression to look at them. But the type of data we normally have are discrete events that we just turn into probabilities. So these are bounded and will not follow one of those distributions, probably follow something similar to a logistic regression. And why do I say that this stuff is important to keep in the back of our minds is because if we run something like an ANOVA or simply a regression, it's going to estimate values that do not exist in your data and could not possibly exist. For example, they might overestimate over 100%, which is not possible. They might not capture all of the variance within responses. And then if we kind of aggregate all of these things together, it leads to creating differences where some might not actually exist. And we have no way of knowing. There's no way to correct after the fact by just saying, well, I'm not going to report this part of the data because your model went on the assumption that this is what should actually be going on. Okay, so what is my proposition is that we should be using Bayesian mixed effects models to do this, which I know might sound complicated, but as I'll show you in a second, is actually much easier and less likely to introduce researchers' degrees of freedom. So mixed effects models have a lot of advantages over the traditional factorial models like ANOVAs. First of all, if your data is completely unproblematic, they'll give you the exact same results as the more simple analysis. They also permit all types of data, so ordinal, count, normal, it doesn't matter. They can incorporate much more complex data and designs, and it also handles missing data much better. So for example, in an ANOVA, if one of your participants didn't see one of the videos, you just cut the entire row because you can't aggregate them the same as everybody else. With a mixed effects model, all you do is you know that in that trial, that participant doesn't have a value, but they have values in all of the other ones. So it saves you on power and also makes inferences a lot more correct. Not only that, you can have unbalanced models. So for example, one condition might have fewer people or fewer videos. In ANOVA, even though I've seen reported tests like that, it expects everything to be completely symmetric. And the reason why I'm focusing on Bayesian, I'm not going to spend too much on this, but it has a lot of advantages to over frequentist tests, especially given that we're doing a lot of exploratory research instead of just confirmation research. Okay, so mixed effects models can do something that your ANOVA can't, which is understand that your different trials and your different participants might respond differently and have different impacts. For example, in an ANOVA, all of these movies, which are clearly different, would just be treated as trial 1, trial 2, 3, and 4. So they would be basically seen as equivalents. But even if we give them this label, they are clearly completely different movies and might all have different impacts on participants or different impacts on different participants. The same with the participants themselves. Some of them, even though the ANOVA thinks they're all identical human beings, we know that maybe one of them is not really paying attention. Another one is being super cautious and super aware and might have a much more narrow variance of responses. Others might have different mood, which is impacting their responses, and so on and so forth. So this is completely ignored in the current models that we are running, but not in the more advanced ones that will be showing in a second. And all of this, again, I know that time constraints are a problem now, so I'm not going to overview the entire field of signal detection theory. All you need to know is if you're asking people to discriminate between two types of things. So like two categories, like is something old or is something new? Do you like something or not? You can use signal detection theory to do so. If the answers they're providing are basically yes or no, something binary, we can analyze them in such a way that they tell us how accurate they are at making these types of decisions. So in our case, how accurate are they at discriminating lies from truths, and also if they are biased towards picking a specific response over the other one when the signal is not very strong. And the way we can incorporate all of the fancy things that I just mentioned is with what are called probit models. Those of you that have used logistic regression already know what I'm talking about. Probit is just a different form of the logit function that has, as you can see, the thing I plotted here. They're basically interchangeable. The only advantage is that we, well, not me, but people have found that mathematically, probit models are akin to signal detection theory models. So if you simply run your models using a probit function, they are akin to the signal detection theory models that we want, meaning that the output is going to give us bias and discriminability or sensitivity or accuracy, as any way you want to say it. And that's it. Basically, we're just modeling the data using probit models, and it's going to give us the results that we were looking for anyway in those 4 analyses earlier without having to do any weird manipulation. And I'll show you exactly what I mean. So in terms of the data processing, all you have to do is have long format data, meaning that instead of having one participant with a single row, each one of their responses is given its own individual row. And make sure that you have something like 1 equals truth, 0 equals lie, and the same for their answers. So basically, if they pick the truth, it's a 1. If they pick the lie, it's a 0. That's it. You don't have to calculate accuracy, don't have to turn them into percentages, don't have to do anything. Once you have this, you install RStudio, you install a few packages that I've listed here, and then basically you're good to go. I'm gonna skip the slide on priors because it's not really that relevant. And once you do that, with a few lines of code, as I show here, you can run one of these fancy models. So just briefly, this captures the first parameter is your bias. The second one is the actual accuracy. And then we're also incorporating the variance between people. So maybe one individual responds differently from other individuals. And we're also capturing the variance and uncertainty due to the stimuli. So one video might be affecting everybody more strongly. So this model takes that into account when it's giving you the actual accuracy and bias. And then we just report the values. In this case, we find the first one is the bias, and the second one, I see that accuracy is essentially 0, because again, people are not very good at detecting deception. So we see if we convert this, that people are truth biased. So essentially, they have a liberal way of responding to the videos that they are seeing. They're more likely to simply select truth. So basically, what everybody in this community is already aware of. And then we can also plot the data nicely. Now, I've also extended this, but I see I'm running out of time. So you can easily incorporate more complex models than we have at the moment. So if you say, oh, you just basically showed me a t-test, that's not so useful. My designs are much more complicated. No problem. You can easily incorporate the between subjects factor, and you just basically add 2 things within the line that I showed you earlier. And the output, you will get differences in bias between each of the conditions that you've added, the same as differences in accuracy. Again, you can easily plot them, and you can extend this to between factors or even their interaction. So once you start adopting this, and again, you don't have to do anything extra to the data, you can easily run these very complicated models and have much more insight and know that you're reducing the risk of error that you can have. Not to mention that this is just the scratching the surface on the myriad models that we can build related to signal detection theories. For example, we have models that can incorporate both the veracity and confidence responses at the same time. We can look at the honesty scale instead of just dual yes or no or lie or truth responses. We can also incorporate chance. So basically, you can tell the model the chance or the guessing that people would do would be 50%. Take that into account when you're estimating the actual sensitivity that people have. So again, and this is super easy to do within these types of packages. So yes, hopefully that'll give you some insight into why with just a few lines of code and something that you can set up within, let's say, 10 minutes, you could be analyzing your data completely differently, incorporating all of this extra information that normally simply gets discarded. And not to mention, that might be interesting for some of you, is that Bayesian analyses are sample agnostic, meaning that even if you have very small samples, it will still run. It will just have bigger uncertainty around the parameters, and it will tell you this when it's running it. Okay, that's it for my time. Sorry that I was a bit over. If you want more, I have papers that kind of use these types of techniques, and I'm looking forward to your questions.